are the kids actually the same as the adults? Because if these evoked potentials really reflect direct inputs.
But it is interesting that we can take signal principles we learned from the brain surface and apply it to stereo EEG.
And so there's specific models now that predicts the circuits. There's a lot of specific models that predict the neural.
Welcome to Stimulating Brains.
I met Dora Hermes and Kai Miller at the Roton de Oliveira course on functional neurosurgery and neurology at Mayo Clinic, Jacksonville this February, and was lucky that we could find a time to sit down and talk about their fantastic work in invasive stimulation, signal recording, modeling, and signal analysis. Both Kai and Dora are super smart researchers that care deeply about how to actually do things and have been leading the methodological camp of signal analysis for years now. Dora has a mathematics background and Kai studied physics, including a PhD in physics, before becoming a functional neurosurgeon. Together they have become a powerhouse and each lead a lab that heavily collaborate at the Mayo Clinic in Rochester, Minnesota, where both are associate professors. Last year, both of them last authored a paper each at Nature Neuroscience, each with remarkable and groundbreaking findings about pretty different topics. And with this prelude, I'm quite sure you will find the conversation as inspiring as I did, and would like to thank you for tuning in to Stimulating Brains. Thanks a lot for taking part in this, Dora and Kai. I think this is the most beautiful setting for a podcast recording. We're here at the beach in Jacksonville, Florida, met each other at the course, and spontaneously, it's also the most spontaneous episode we ever done so far. And usually to break the ice, I before we get into science, I ask always about hobbies and free time. So what do you guys do when not involved in?
You first, Dora.
Me first. I mean, there's not a lot of free time, right? So that's one of the. We have two little kids, two boys, age 8 and 12. So they take a lot of our time. But when we, the little bit of time that we have, I like running, cooking, hanging out with friends, reading a little bit. But that's about how much time. Making Halloween costumes once a year.
Makes sense.
Yeah.
Oh, you make them yourself.
Yes, yeah, once a year, and I try to block some weekends for that. But that's
fantastic.
About.
It's like a project months out.
Okay.
Yeah.
She's making it months out. Yeah.
And you guys.
I play tennis. I spend a lot of time coaching our boys who are right there doing their math. But
yeah.
I had them across the street earlier today. So I spend a lot of time, either with Dora or the kids. And by a lot of time, I don't, because of the surgery. I basically, it's surgery and science is not science is 90% nights and weekends.
A hobby in a way.
In a way. I mean, I spend a lot of time doing the science, obviously at work, but a lot of the science at work is the things around doing the science.
Yeah.
And of course I like, I like doing the science too, which means if I want to squirrel away some time, that's weekends.
And you surf, I think. You once
yeah.
With Nolan, right?
I surfed a lot growing up. It's hard in Minnesota now, but we travel because of conferences. For example, last week we were at the Peds Neurosurgery meeting in Hawaii, and nice. There's a friend of mine who also surfs, who's also a pediatric neurosurgeon, so we went surfing 4 or 5 times last week.
Fantastic. Cool. Who were your key mentors in your career, and also maybe turning points that led you to where you are now?
So I did my PhD with Nick Ramsey, who was a fantastic mentor. He was my PhD advisor, and he would always ask questions and questions and questions. So he was a really good person to work with. And then during my postdoc, my primary mentors were John Winnemer and Brian Wandell. who had a very different style, but also extremely supportive and great to work with. I learned a lot from both of them, and they were also, the postdoc period is always a difficult period.
Yeah.
You try to get your own funding, which is not always successful, and they were very supportive in teaching that and getting through that kind of challenging time, and were interested in very similar topics. So it was really great to work with them.
Fantastic. And when did you move to the US?
So I finished my PhD in 2011, and then we moved to the US as well in 2011.
Okay.
I think you moved to the US in fall of 2010.
I visited Seattle in the fall of 2010.
Well, you lived with me there. Jeff Ogeman invited her to come to the lab for a while, and that was when we were together during my last year, and then her visa was running out and Max was on the way. So
oh wow, okay,
that's when she moved.
Fantastic. Okay.
Yeah, so that worked out really well.
It did, yeah. And then she actually finished her PhD with Max on her belly. She would wear one of these, they have these carriers that go on your belly, and so she'd stand at a countertop in our apartment in Palo Alto with Max on her belly and just sit and type when he was a small baby. And she finished her PhD, I think, when he was 2 or 3, as old as your son.
Wow.
When he was 2 or 3 months old is when she finished.
Yeah, they still sleep a lot when they're 2 months old, so they allow you to do a lot of typing, and they love just sleeping in one of these carriers. So there was a lot of that worked out.
I can relate to our 2 months out old. It's also called Max, by the way. So fun coincidence.
That's great.
Yeah.
So okay, and for you, Kai.
I mean, I had a interesting childhood, but I think. My dad was really into science. Okay. He's a banker, but he was into science, and so he would talk to me. I remember talking to him about imaginary numbers when I was a little kid, and he would always he read these popular physics books. Stephen Hawking and Mr. Tompkins in paperback. So that's what got me into physics was these my dad and his bookshelf, as it were. And then when I went to college, there was a guy who was a mathematician who was really into James Joyce, named Patrick Ledden. He's subsequently passed, and I have a big aspiration of mine is one day to get to go back to UCSD, and they have named an auditorium after him at Muir College in San Diego, where I was an undergrad.
Oh wow!
And my goal is to get to go back and. I haven't thought, and
you did
and get to
undergrad. That was bachelor in physics in San Diego, right?
Yep.
So,
yeah.
And then you did the master's in physics and a PhD in physics afterwards too, correct?
Yep. Yeah. So I went to from UCSD. I went to at UCSD. I worked with this guy David Kleinfeld. I don't know if you ever heard of him or met him. He's a physicist who does neuroscience. He just does very careful experiments. He's a very careful thinker, and he told me I should go work with a guy named Fred Ricci at University of Washington, and that didn't work out, but I wound up interacting with first a guy named Mike Shadlin, and then Raj Rao, and then Jeff Ogeman. And Raj Rao was a computational neuroscientist who had some interest in BCI, and at the time I wasn't so much into it, but I said I'll go learn about EEG and stuff so we could do it. And that's when I met another neurologist who introduced me to George Ogeman, who's Jeff Ogeman, who's actually Otto's godfather, is his dad. And he said, well, I'm going to retire soon, but you should work with my son. And so that's sort of what got me into neurosurgery, was this guy, Jeff Ogeman, who I had all this access to working with him, and he had a background in physics too. And I just we developed this research program when he moved to University of Washington, and he's still a mentor of mine. I mean, we saw him at the PEDS meeting last weekend in neurosurgery and also in science. And then I did my PhD with a guy named Marcel Denis, who's a theoretical physicist who does condensed matter physics. And then I did my neuroscience PhD with Raj Rao, who's this computational neuroscientist there.
And then after that, you decided to go into medicine, right?
No. I went to Seattle to do
MD PhD.
MD PhD.
Okay, got it.
I had wanted to be an astronaut, and I was going to do emergency medicine, but NASA was sort of winding down the in-house space programs. They don't have shuttle launches or anything like that anymore. And I got a lot of exposure through Jeff Ogerman to neurosurgery, and I knew I loved operating. I never thought I was going to do neurosurgery. In fact, Dora was the one that that told me to just do it. At the end of the day, I was going to do radiology and do neuroradiology.
Okay, interesting.
Which is awesome.
Yeah.
I work closely with neuroradiologists now, and
yeah.
it seems like. But I had no interest in the rest of the body outside of the brain, at least not professionally, and so I wound up doing neurosurgery. I went to Stanford, and I had a number of great neurosurgical mentors. Jerry Grant at Duke, who we're going to go visit, and Casey Halpern, who I know you know well, because we both interact with him together. And a guy named Griff Harsh, and another guy who was my chairman named Gary Steinberg.
Okay, fantastic. And so when you became a neurosurgeon, why in pediatrics and why functional? How did that come up?
Oh, you asked about turning points.
Yeah.
A big turning point was another mentor of mine, Nick Ramsey, who was her PhD advisor. He's introduced me to Dora. So the best thing I got out of science and life in general was because of that guy.
Fantastic. And when was that again? When you met in your careers? You were finishing your PhD, and you were.
I was.
That was several years prior.
PhD.
She was in the beginning of her PhD when we
it.
first met.
Got it. Okay.
We did long distance. We had a long distance relationship for 2 years.
Okay.
Yeah.
And then I visited his lab. And
Okay.
She was one of like 5 people in the world that would think I was cool because I was a scientist.
Okay, fantastic. And then so why functional, and why like epilepsy in pediatrics?
Well, that's a complicated story. So functional fits with the, I'm interested in understanding the large-scale circuitry in the brain, and physics gave me a good background for that, and functional is an actual extension of neurosurgery into understanding how the brain works, right? It's functional neurosurgeons are the ones that study circuitry in the brain, and I figure if you're going to do neurosurgery and neuroscience, that both of them better make you better at both, or you're going to be worse than other people who focus on one, because those people are equally intelligent and equally hardworking. Mm-hmm. But actually, the type of surgery I enjoyed the most during my training, and that I still do some of, is basically awake brain mapping. And so that's not, I don't think I'm going to contribute a lot intellectually to that part of neurosurgery, but it's the part that it's technically the most fun for me. And
with that you mean electrical stimulation of the cortex?
Yeah, electrical stimulation with patients awake, but then there's also this thing where when you're taking out a brain tumor, you're finding the electrical boundary by stimulating and interacting with the patient. And then there's a tactile boundary that you find as well using your neurosurgical instruments. And the art of that is the part of neurosurgery that I enjoy the most. So functional neurosurgery, a lot of what we do is you have to be technically proficient, you have to be precise, and extremely avoidant of errors. Right? You want to be as accurate as possible with as little chance of anything going wrong as possible. And so I spend all day thinking about that. And so there's a practice to it, but not as much of an art to it as other types of neurosurgery. And so I enjoy both. And I actually did a fellowship in the Netherlands, where she's from. We went back one year of residency, and my 5th year, and I did a tumor fellowship in awake mapping with a guy named Pierre Robet, who is a Belgian guy, but I guess your background is more in neurology than neurosurgery, but he's wonderful. And then there was a pediatric and epilepsy team there. And so we went back at the end of residency. I was awarded this thing called the Van Wagenen Fellowship. Mm-hmm. That's a really nice program. If any of your listeners at any point are neurosurgeons, it was sort of a key turning point in my career, was getting this award, being able to go to the other side of the world and learn the techniques they had in open surgery for epilepsy for kids, because every kid that needs epilepsy surgery in all of the Netherlands should go to Utrecht, this one pediatric hospital they have there.
Got it.
And so we went there, and I did science with Nick Ramsey, and I did surgery with the epilepsy and pediatric teams there, and they've got a great collection of surgeons. So
how did you like Europe, and how do you relate to the US? I'm sure you have acclimated by now. Like, what's the do you ever think of moving back, or consider I don't know, spending a sabbatical there? Or, yeah.
Oh yeah, I think we would love to move around a little bit,
Yeah.
but right now things are. Mayo Clinic is fantastic, and there's in Rochester, Minnesota. There's such a great neurology team who we collaborate with right now. It's also like just a very good city to live. It's a small town, but it's really good for families. So for now, this is a great place. But I don't think I would have moved here when I moved from the first time from the Netherlands to the U.S. That would have been maybe a little bit, moving to a place like the Bay Area or Seattle was much easier when we just got here, compared to moving to Rochester, which is much smaller.
And Dora, you have a background in engineering. How did you choose to get to the brain, into the brain?
So I have a kind of a strange undergraduate, because I did math for 2 years, which is in the Netherlands a full-time math undergraduate. You don't do anything else.
Wow.
But it was theoretical math. So after about a year and a half, I realized that it was a little bit too theoretical for me, and I wanted to apply it to some things. And so we had like just one very small course on some modeling, and I loved it, and applying it to biology. And so I needed to switch. So I switched to psychology and neuroscience at that time, and finished a neuroscience undergraduate, and then a neuroscience master's, which you do in the Netherlands before you do a PhD. And then starting to look at brain signals was kind of a natural. Whenever I remember the first time you get to measure EEG signals or fMRI signals, it's just fascinating that you can actually measure human brains. So I just knew I wanted to just measure as many different signals as possible, such that we could actually learn what kind of dynamics are going on in human brains. Yeah,
fantastic. And so Kai, on the one hand, you have, I think, 13,000 citations and an H-index of 54. Just Googled that. And numerous publications, and then you're also a full-blown neurosurgeon, and you have 2 kids, and you told me, however, you still code a lot yourself. So I think you develop electrophysiological methods, right? Really do hardcore, like new methods development. How much time, and it's hard to delegate that type of work, you said, right? Because it's really complicated and involved. So how much time do you get to code and do that, and how does that all work out? It's hard to imagine somehow. But,
yeah, I mean, look, anytime you're a doctor, so you understand, and you code, so you also understand. But anytime you're taking care of a patient, you're doing surgery, like all of your attention,
of course,
is on that first and foremost, always. But when I'm not doing that, if I'm out, screwing around with the kids playing tennis, or I don't know, if I'm in the shower or whatever, I'm thinking about the problems that I'm interested in. And it always goes from thinking about the general problem, trying to frame the scientific question that you think is important. And I don't, I think some people are very interested in a particular modality in the brain or a particular disease. For me, what's fun is the signals that we measure, right? And I measure those in the operating room, and I'm lucky to have some wonderful graduate students and postdocs, and be able to work with Dora and the Nuri Inche and Greg Worrell. We sort of have a big team at Mayo, and so I when I'm not operating and directly taking care of patients, I'm immersed in this environment and I'm thinking about problems.
Yeah.
And then I go from trying to frame the problem best I can, and then I usually start kind of writing things out just symbolically on, I keep either notebooks or on a whiteboard in my office, and then the code is the end step.
Yeah.
And so for me, it's just I go directly to that, or I tinker with data and I get sort of wrapped up in something, but that's usually episodic. So it's a weekend where I'll kind of go manic on a particular scientific problem, and a lot of it comes from conversations that I have with Dora about some problem that she's interested in, and I'm interested in the fact that she's interested in that problem, and then we'll talk about it, And we'll talk through some strategy, and then the code is just articulating trying to interpret the data that we measure,
Sure.
as far as I'm concerned. So I think most people that are real coders would look at the things that I write and say this is sort of primitive and there are more efficient ways to do it. But if you take the math...
Yeah, exactly. I mean, that's not what this is about, right? But I mean, to me, it's even much more impressive that you apparently start on a whiteboard and then only use code to finalize things. Usually the other way around, I have to implement stuff and visualize things to understand it and follow it. But it's great that you...
I mean, I think, I mentioned my PhD advisor in physics. He really... he's a Dutch guy, and Dutch people are, they say they're direct. Other people would say they can be rude or whatever, but I always, I clearly have gravitated towards them, right? I mean, it's the most common language in my house, and I don't speak it, but, or don't speak it well. But he really hammered into me, this is how you think about problems, right? If you do what these people that are theoretical physicists have done and experimental physicists, what you need to do is you need to articulate the boundary conditions for any problem that you have, and then express a set of algorithms that address those boundary conditions clearly, and then the analysis of the application of that in code or whatever is just that's sort of the theorists, at least, kind of like they look at that as I don't know, they look down on that part as the end. So that should be the part that's trivial. It's not trivial for me, but that I learned that's what I should aspire to.
That sounds great. And then you also mentioned that each Friday you are on a call with Klaus Robert Müller, who is a famous brain-computer interface expert out of Berlin. How did that come to be? Sounds like a great standing meeting.
Yeah, I first met Klaus when I was a graduate student. I think Raj knew him, and I met him at some conferences. And the truth is that we would kind of just hang out and drink beer together and talk about some problems. And it was clear to me that this guy's really smart.
Yeah.
And it intermittently kept in touch with him. In addition to doing brain-computer interfacing, which was how I initially interacted with him. I mean, he's one of the top machine learning guys for decades, and his recent work is in, it's in quantum computing and the synthetic chemistry and sort of a wide variety, but he's making major contributions in all these different fields. And what happened, the way that I started interacting with him, I guess after we moved to Rochester, he'd had me come talk at a conference in Korea. He has some joint appointment thing in Korea, and he had me come talk about the work that we were doing before we moved to Rochester. And then something like a year and a half, or maybe even just a year later, because COVID hit right after we got there, I was working on this problem related to cortical vocal potentials. So you stimulate one brain area and you measure another brain area. And this was work I did with Nick during my postdoc in Utrecht, and this is what Dora's first R01 was on, and what a lot of our work now is on. And I was trying to think about how to, because it's this very large end-to-end problem, right? So let's say you have 100 electrodes that you're stimulating at, and 100 electrodes you're measuring from. If you look at all the comparisons, that's 10,000 comparisons that you're trying to make.
Yeah.
And if you want to simplify this algorithmically, you first have to say, well, how can I make this a tractable problem? And what we realize is you can look at you can think about it as stimulating one spot and measuring everywhere else, but inversely you can also say, well, if I look at one spot and measure everywhere else, what are the flavors of responses that we get? Because one particular brain area, if you stimulate a bunch of other brain areas, the shape of that response, of the voltage signal you get in time, is very different depending upon where else you've stimulated, presumably because the types of connections that you have are different. But it's constrained in the sense that you're always measuring from the same place in the brain. And so when Dora and I were working on this, we were talking about it, and I was able to constrain this down to a problem that I thought was a hierarchical clustering problem.
Yeah.
So you measure some stimulation from stimulating some other brain site at the place you're measuring from. You measure 10 of those, but you have 10 from these 100 other sites, And so you can say, well, first of all, is there a consistent pattern, which is when I stimulate at one other site 10 times in a row, are there 10 consistent patterns? But then, are those 10 patterns similar to anywhere else? And so you have this hierarchy that's set up. And I thought, well, I articulated it well. I articulated what the problem was well. And I'd been talking with Dora about it, and I was looking at it, and I thought, well, there must be just some off-the-shelf solution. So I looked for an off-the-shelf solution, couldn't find one. I contacted Klaus, because he's, I figured this is the smartest guy I know. And I said, this is the general problem. Do you have a minute to talk about it, or do you? And so he met with me. It was over Zoom, and he said, well, I can't think of a problem, but the way you're starting to formulate things is similar to a field of statistics called functional data analysis, which I hadn't heard of before. And what we did was we just started meeting regularly, and I treated it as if, as another postdoc or something. Yeah. And I hope I can keep doing this. I had a cluster of time right when COVID hit for about 3 or 4 weeks, and that's when we started this. And we came up with this new way of doing sort of hierarchical clustering that I think has general applicability, even though we did it in brain signals. And so we just sort of kept meeting in between. We've actually been to visit him a couple of times in Berlin since. But mostly it's just that, I think he's really fun to interact with, and he thinks about things in a way where I learn every time we talk.
Great.
And Dora does a lot of that, and the boys love him because they, they happen to have a particular talent for mathematics. And since I've said, well, Klaus is the smartest, physicist, mathematician that I work with, Max is always trying to jump in on the Zoom and make funny faces. And
fantastic.
Yeah.
Love it. And Dora, I think your work, you mentioned you were interested in any type of signal you could get your hands on, but also I think your work also combines electrophysiology with imaging quite a bit, right? So I think often collaborative project with intraoperative EEG data, so EFIS data, but then also tractography. How would you, if you had to, in a nutshell, characterize your focus, maybe as opposed to Kai's or together with Kai, what do you want to, what do you mainly work on?
So the thing is that we can, we have this access to, working with neurosurgeons and neurologists, we have this access to this unique set of intracranial EEG data, where we can learn something at sparsely sampled nodes in the brain. There's always, maybe up to 256 electrodes, which might seem like a lot, but they're still placed in pretty small areas. And so the only way to connect kind of our field in which I see it to the rest of the world, basically measuring fMRI, diffusion imaging, EEG, those types of signals, non-invasively, is by combining them. And the other thing is that it gives us a really nice way to, this combination of techniques gives us a very nice way to both sample very sparsely with a lot of temporal detail, and but also integrate that with this large body of other data that already exists, and but we know a lot more across a lot more subjects that are typically healthy, so we can compare our data and understand also what the neurovascular coupling is, for example, that gives rise to the fMRI signal, which is extremely essential because there are so many little details in variations in fMRI that can be explained potentially by the underlying physiology or by changes in the vascular properties, and so understanding those relationships was essential at first. The other, so that's from a fundamental perspective, that we want to tie these networks that we can measure, or for example, you can have models developed for fMRI, and then you can apply them to the other and understand how the different signals correlate. The other more clinical translational purpose of this is that if you see a patient and you have to implant an electrode, either for brain-computer interfaces or for deep brain stimulation in a particular region, to either stimulate the brain or to read out the signals.
Yeah.
You have an infinite amount of options, basically, of where to implant that electrode exactly. And so you need some level of imaging, either from a functional fMRI perspective, to understand where you have to place an electrode for brain-computer interface purposes, to make sure that you're implanting on a functional region, that actually has a reliable signal during what you want to measure, Or for deep brain stimulation, you would want to implant it in an area where you're actually going to get outputs in the network that you're interested in. And so I think that combination, that's the kind of the clinical translational aspect of it. I can explore these things from a very fundamental perspective, but I can collaborate with people like Kai or with some other neurologists that we work with to really translate this to practical purposes, which I think is fantastic.
Yeah, very translational. And so in a way, the imaging part fills the gap of the where more than, or like at least that's one purpose of the imaging in your work.
Yeah. So one of the purposes is really filling the gap of the where in kind of the translational component. Yeah. The other aspect, which is what we've done in the past as well, is in visual cortex. There's been a lot of models for vision that have been developed for the bold signal. Yeah. But when we have electrophysiological measurements, we don't only have one signal. We have all the different frequencies in the field potentials, broadband, gamma, alpha, sometimes different oscillations. We have evoked potentials. We have all these different signals that can tell us different things about neural computation. And these models that have been developed for fMRI have pretty specific parameters in them, such as amount of compression, the amount of which is related to the amount of surround suppression, for example, or suppression in nonlinearities in contrast response functions. So it tells us very specific things about the computations of vision. Now, when we translate these models to the electrophysiological signals, they might describe one type of signal extremely well, but others not so much, which means that other signals are related to different processes that we can then quantify using different types of models or modifications of those models. So it really gives us a way to get, this combination gives us a way to get one way of thinking about the computation in vision, and then we can combine that with different models that capture different types of brain signals and tell us complementary information from different modalities.
Fantastic. And so both of you had a paper last authored, like two of them in Nature Neuroscience last year, right? Congratulations, that's really fantastic. So and we could maybe focus, like briefly speak about both of them, and can maybe start with Dora's. I think in this one you combined a lot of evoked potentials, probably also using some of the methods that Kai and Klaus or you all developed together with 74 patients across child development. Can you summarize the study a bit?
So we've been collaborating for a long time with Utrecht, who have been collecting these single pulse stimulation data for the last 10 years. Mm-hmm. And so they have done this exact same type of single pulse stimulation experiments with intracranial recordings, where they stimulate a pair of electrodes with a very brief pulse and then measure the propagation throughout the rest of the brain. And they've done this across a population of age 4 to 54 years old, I think. And so they had this large data set, and when you started looking at these different evoked responses, they were very different across different types of connections, and one of the questions that we were asking is, like, are the kids actually the same as the adults? Because if these evoked potentials really reflect direct inputs from one area to another, we know that there's a lot of structural changes between these areas caused by myelination, for example. And so that evolves over this kind of age span. And so we just wanted to know is that if those changes are there, they should generate different types of latencies. Yeah. And so the earliest response, there's many different waveforms other than the early response, but the earliest part of the response is hypothesized to be related to direct cortical connections. So we looked at subsets of regions that are directly connected across the, for example, the arcuate fasciculus, superior longitudinal fasciculus, the temporal parietal Aslan tract. Okay. And we wanted to understand like what the rates are at which these things are developing. And so we looked at the earliest response and quantified the earliest response latency, and we saw that it is about twice as fast in the kids compared to the adults.
Interesting.
And so that's actually a really large difference from 50 to about 20 milliseconds. Might seem like a small difference, but it's an order of, it's like twice as fast. And we saw this across, and it kept, when we started to fit different types of maturation curves to that, it kept developing until the age of about 30 to 40 years old. So it was a really slow maturation curve that actually fits the diffusion imaging data extremely well. Whereas from previous evoked potential studies, we would have expected that maturation would be kind of done by the age of like maybe 15 or so, and definitely by 18. But it actually has this very long time scale of maturation that is really interesting.
Did you go beyond 30 and 40? Probably not, right? Or
so our oldest subject, given that our oldest subject was about 54 years old, we could see that some areas plateaued, but we could not capture what happens on the aging end of things. So we know that we kind of see that developmental curve, but aging I don't
makes sense.
Yeah.
And so the degree of myelinization from DTI, you also had that in the same like subjects or similar age spans?
No, we actually had we used an atlas because we didn't have diffusion imaging scans in all of these subjects. We would have loved to have that, but we didn't. It's a clinical population, and so we just had to work with the data that were available. And so what we did to estimate the conduction velocities across these fiber bundles is we used a diffusion atlas, and we basically mapped that to every individual subject to get an accurate estimate of the length of each fiber bundles given where the electrode were placed. So we could basically calculate a conduction velocity for each fiber bundle per subject, and then we looked at that in addition to just looking at the latencies. So we couldn't imagine, but that's the basic approach that we could take in this case.
Fantastic. And then Kai, you also again had as a second paper. You were last author there. What is yours about? Or what? I think you're both co-authors on both, but
so. Mine relates to motor function, but our group, or at least my lab is called cybernetics and motor physiology. It's mostly because motor's an easy dial to turn. You ask people to perform different movements, and you can, if there's differential representation of the body, you can make different areas become active. And so work that we had done a long time ago when I was a grad student, we sort of found that if you look at the signal from the brain surface, electrocorticography, so pads of electrodes on the brain surface, you have these brain rhythms that people talk about a lot. And the topic of my physics thesis was the discovery that in addition to oscillations, there's also something that has 1/f structure. And what that means is that the power in the signal falls off like 1 over the frequency to some exponent. And that's important because there's no oscillatory property of that. So if you look at it in time, it looks like a random walk. And we had shown that in electrocorticography, and then we had found that if you capture this what we call broadband, the power law activity in that voltage trace, if we capture that broadband, you could do things like resolve fine representation of different fingers and that kind of thing in electrocorticography. And there's been a transition in how we identify where patient seizures are starting from in epilepsy monitoring from these electrodes that go on the surface of the brain, electrocorticography, to electrodes that penetrate throughout the brain and let us sample from all these deep structures and identify basically seizure onset areas that we hadn't been able to with electrocorticography. And these types of measurements in Europe actually go back to Jean Taylorach, somebody in France, 50 years ago. And there have been pockets of places where stereo EEG or these depth electrodes have been done all along. But there's been a transition to this in the U.S. And because I do this with and most of I've got 2/3 pediatric practice, and most of the kids that we monitor to figure out where the seizures are coming from, their stereo EEG. And so I thought it would be an interesting project to look at first whether or not you just can capture these same types of broadband changes in the voltage trace and that those correlate with local cortical activity. And so, my first graduate student, his name is Michael Jensen, I wanted him to do that. And so we started out by just saying, well, why don't we have just a simple task to try to get the different somatotopic areas of the brain, the different representational areas of the brain for movement, see if there's some differentiation in them. And I wanted to give him kind of a dumb project to start. Dumb not in the sense that it's unimportant, but dumb in the sense that it is relatively unsophisticated neuroscientifically, like a control from which we can move forward. So I said, well, we know that there's this representation of different areas in the body for movement in different parts of the brain, in the precentral gyrus. And that's really been established well on the surface of the brain, going back to Penfield and other neurosurgeons, Penfield, Woolsey, and then...
Osler as well.
What's that?
Osler, I think the Penfield's mentor in Germany did the same stuff before as well. Yeah,
absolutely. And so I said to Michael, why don't we just we think that the representation is just going to extend down into the sulcus, but we can actually measure that. So with the stereo EEG, so Michael basically, I had him do a hand, foot, and tongue task, and I wanted to use this as essentially a training task to get him to teach him the tools that we would need. We're sort of a tool building lab. To then go ask more sophisticated questions about the motor system and do brain-computer interfacing, all of which we've done, but none of which we published because this turned out to be more interesting than we expected. Because when Michael looked at this representation, he found that there are these somatotopically specific areas. There's an area that's just hand, an area that's just movement of the tongue, there's an area that's just movement of the feet. Follows the classic representation that we knew from fMRI and from electrocorticography. And he came to me and he said there are these other regions that seem to be active no matter what part of the body the patient's moving and which side of the body it's moving on. I think I'm just doing something wrong with the analysis. We did the most simple referencing scheme so we could reduce the problem to the most simple analysis possible. So we knew it wasn't referencing, but he said, I think I'm screwing up somewhere. I said, you probably are screwing up somewhere, but let's just see if we continue to see this pattern. And we saw it in, I think at that time it was something like 13 patients in a row had these areas that were somatotopically not specific. And so we said, well, it looks like there's something different here. And there are these areas that look how we expect premotor areas in other brains and other parts of the brain to act, but they're down in the depths of the central sulcus. And so this association area that Michael discovered along with the rest of us is, we call it Rolandic motor area. And what's kind of interesting is that folks using fMRI at another institution at WashU seem to find that there's a network of areas that interact that maybe serve a little more sophisticated function than had been recognized previously in these in the precentral gyrus. And I think what we really established is that there's these non-somatotopic specific areas. And while you can't resolve, the spatial resolution of fMRI is a little different than what we have. You can't resolve certain types of network behavior well. I think we found something that's this robust new area in the depths of the precentral gyrus, and that this emerging work in functional imaging may provide some explanations for what the role of it is. And so we're working with that team at WashU now with John Willey and Peter Brunner. On trying to understand this network a little better.
Very interesting. So essentially the classic, it's a similar finding came out the same time as the also Dosenbach paper where it's really about these, like the original Penfield's homunculus was broken up. Right?
It's the general organization is there. Somatotopic. That Dosenbach, that's WashU.
Okay. I know. I know. But essentially, it's a similar finding, and both of your papers came out the same time.
we both put them up on our bioarchive within a month, and they both got published within a month. And then now we're trying to sort of collaborate, and it's
electrophysiologically.
It's robust electrophysiologically.
Very interesting. And what types of movement is that area active?
Everything we've looked at.
Okay,
So
the
movement
truncal
of both
complex.
sides of the body.
Okay.
Anecdotally, truncal and speech. That wasn't in the paper, but anecdotally, that's also there.
And also like these precise finger movements, or is that really more respected to the classical?
You know, the differentiating individual finger output, finger representation, so breaking up, let's say, hand area is a little difficult to do because I'm not putting in stereo EEG electrodes to sample.
Sure.
I mean, usually not. Sometimes seizures seem to start from there. But usually we have these electrodes because we want some sampling of motor areas on electrodes that are on their way to the insula, because there may be some motor component of the seizures. But none of these things are placed. I don't do any electrode placements for pure research with these stereo EEG patients. They're all clinically indicated.
Yeah.
But it is interesting that we can take signal principles we learned from the brain surface and apply it to stereo EEG.
Yeah.
Interestingly, we're also doing some similar stuff with DBS, I think I've told you about, where these broadband spectral changes seem to resolve representation of some kind in the thalamus. And Brian Clausen, who is actually at this meeting, I really want you to meet him because he's a big fan of lead DBS, and your work has really guided a lot of how we think about targeting for DBS at Mayo. And Brian Clausen is, he's the guy for that. But he found that you have these broadband changes in thalamus as well from our, from the ring electrodes and microelectrode recording in DBS. So it's a general property of the brain, this broadband phenomena. And representation is tougher with stereo EEG, and with current technology, we're not getting, broad spans of the thalamus to look at representation, but emerging work may show something different.
In his talk, I think Casey Halpern, whom you worked with, who was also on the podcast before, often describes his operation room as an electrophysiology lab, but he gives you the credit that you're the reason that it's that way. And I think your own OR is also a lab with a lot of things. Yeah. Can you describe it, maybe Dora or both of you? How does the OR look like? What makes it special? What can you do there?
Dora likes working with the patients in the epilepsy monitoring unit. She doesn't come to OR.
I sometimes come to the OR and it's really impressive. But I spend most of my time with the patients in the ICU. So But that's because I work most with the stereo EEG cases, which are not as interesting as the DBS cases. The DBS cases, when you see those are really fantastic, and I think I can describe those in more detail.
Yeah, I mean, I think within neurosurgery, most people think of DBS as a not technically nuanced surgery because you're putting in. But the truth is that every electrode we put in, it's a matter of millimeters. Yeah. So it is nuanced just in a different way than a lot of other things in neurosurgery, like those awake mapping resection cases I talked to you about, which I love. The DBS OR is definitely, the DBS is a subset of what I do. It's, and so for those cases, we're trying to understand the signals that we can measure from different areas of the brain. We measure both field potentials and single unit activity. I have Dr. Clausen in there with me, so a neurologist is an equal partner in every part of what I do. And we also now have bioengineer Nuri Inche, who just came to Mayo, who is there with us in these cases. It's important to note, anytime we're talking about this human research, the patients are in control of whether or not they participate. They're not, I don't consent them. Somebody who's completely unrelated consents them, so they don't know that it has anything to do with the research that we do until after they've already decided that they want to participate. So there's no crosstalk there. But yeah, we take these different techniques that we're looking at, things like ERNA, which you may know about. Yeah. We look at that. We look at, we're starting to incorporate some single pulse electrical stimulation into paired depth and surface recordings. And there's been a lot of great work that people have done in their OR. I think you work with Mark now, right?
I do, yeah. A little bit, yeah.
So Mark, I think, has some similar things. We've talked to him a bit, Mark Richardson. And Phil Starr, and I really followed that model. When Casey first came to Stanford, I was just starting my 4th year of residency, and that's supposed to be a research year, but since I had a pretty extensive research background already, they let me do a functional fellowship, and so I was Casey's fellow right from the start of when he got there. And so we would look at these things together. We did some fun work with patients who happened to be getting awake surgery for OCD, and I've continued to work with with him. So I'm a subcontractor on his OCD work now, and we try to port the techniques over. I really enjoy being a tool developer and trying to understand the signals and understand the neurophysiology more than, like I said, more than diseases or representation. So it's wonderful to be able to work with Casey, who's really passionate about helping and I'm passionate about helping patients, but he's really passionate about helping these patients with these new indications. And we may move into that at some point at Mayo, but most of the things that I'm doing now when it comes to new indications like OCD, I'm doing in partnership with people like Casey. And so we've had people from his lab come to Rochester. One of my graduate students and one of her graduate students, Harvey Wong and Michael Jensen, have both been, and they spend time there in Philadelphia, and so we try to interact a lot. The collaborative part of, I think one thing about trying to develop tools, at least my hope, is that people are really just open to the idea of collaborating, because I can give them things that would be useful and let them ask the questions they want to ask. And for me, the reward is the getting to tinker. With trying to have new methods. I'm sure you can appreciate that, right?
No, I do. I do, absolutely. So many have described you as a really one-of-a-kind electrophysiology crack, I think one thing I find really interesting but have no clue about is that when it comes to measuring brain connectivity by means of electrophysiology, you have criticized the communication by coherence hypothesis of Pascal Fries and Andreas Engel. And can you maybe first explain what that is, and then also in like simple terms, and then why it might be wrong? Or I think it also has been openly falsified, for example, in the Schneider neuron paper. But
I think that's an interesting idea. I mean, I should say that when I first started my PhD, I was looking for gamma oscillations, right? And that was the big thing, and Pascal was really somebody leading that, and I think he's done a lot of good work in trying to understand those, and particularly looking at attention. And in looking for those, particularly in other areas of the brain that were not related to vision, and never finding them, was when we said, well, if there aren't oscillations, but there are fluctuations in power, which is what we started to find, and then we fit those to power laws, and we found that instead of being oscillations, there's completely other phenomena. So I should say that the communication through coherence hypothesis, which I think is an epiphenomena, which Dora can actually tell you about, because when we've written papers on this, Dora was the first author, not me. So I better not talk too much, or I'll be paying for it. The thing is that I went when I was just a sort of an early level graduate student. I went to Nijmegen, where Pascal was, and showed him these ideas, and he said, I think this is something completely different. And he actually went out and told a lot of people about the fact that I had come up with this, and I was just some grad student from the other side of the world. And so he was really generous with that. The thing about the communication through coherence idea is that, and Dora will be able to tell you about that, is that we didn't see gamma oscillations a lot, and it may be that you can use some physiologic tricks, and I think that at the end of the day, they may have been exploiting some physiologic tricks that have to do with lateral inhibition, early visual areas that let you tag a certain pathway, and so there may be some real validity to that hypothesis, but there's nothing essential about the oscillatory nature of it.
Got it.
And so I'm going to let Dora talk, because I don't...
I mean, for the first part of the question is like communications through coherence. The assumption in that case is that you have two brain regions that communicate at a particular clock cycle because they have the same clock cycle. So they have the same frequency. It should be a specific oscillation, which should have a peak in the power spectrum, and those should be coherent between the two brain regions. So there's a number of requirements for this theory to work, because both brain regions have to have an oscillation at a particular frequency. And now at some point, Kai mentioned that he'd talked to we were trying to figure out. He talked to someone, and he said that maybe these oscillations are only there when there are gratings on the screen, And we were discussing that with John Winnemer and Brian Mundell, and we were like, okay, we have to dig into this because we sometimes have these patients with these visual recordings. Why don't we just show them a grating? And then as a control, we can show them a noise image that also has contrast, drives visual cortex very strongly, drives firing rates in visual cortex, drives fMRI bolt signals. And so we showed these patients... We showed these patients sets of gratings and sets of noise patterns. And then what we saw for the first time is that these gratings induce these very strong narrowband gamma oscillations around 50 hertz that we had never seen before in ECOG. In none of our previous ECOG recordings, in motor cortex or in language areas, or even in ventral temporal areas, we had never actually seen these very strong narrowband gamma oscillations. So we were very surprised, that we actually had a stimulus that could drive those. And they were just stationary on the screen. And the idea behind it was that we made them the gratings with different spatial frequencies, because we thought that it may be the spatial layout of the image that would drive it. Now we later fine-tuned this because that didn't seem to be the simple case that the spatial frequency translated into a temporal frequency. That was not the case. So that hypothesis was not true, but we did see that we had very strong gamma oscillations for gratings and not as much for noise patterns. And then we also thought, noise patterns, it doesn't really have content. So let's look at this large image set that we had before that has faces and houses and other objects in it. And then we noted that out of those images, there were many images, most of them did not have any gamma oscillations, but the subjects reported whether it was a face or a house, so they could see the image. So it wasn't even the fact that there had to be some content in the image. There were many images that had content that you could see that did not have a strong narrowband gamma oscillation, but had a strong broadband signal.
Yeah. So in other words, coherence was not necessary for any kind of perception, right?
Yeah, so coherence was not necessary for perception or for any feed-forward propagation of the signal. Yeah. It wasn't an essential component. There were plenty of cases in which it was not there. And we did see this, but we did see for these gratings, we saw very beautiful coherence also. The supplement of the paper shows that a very beautiful coherence between V1 and V4 if there's overlapping population receptive fields. Beautiful coherence between the two areas, but you have to have a particular stimulus that drives that. So if you have, and then,
So it was not related to these two regions talking, but rather both of them receiving a similar stimulus.
Both of them. So we think that these gamma oscillations are generated in V1 if you put a grating on the screen, and we think it's particularly a large grating with the same larger contrast, larger gratings. So it's somehow related to this to these orientation columns responding strongly to the same inputs. Being connected to, inhibiting each other as well with, cross-orientation suppression. And so there are specific models now that predict the circuits. There's a lot of specific models that predict the narrowband gamma oscillations only for gratings, but not for noise patterns, for example.
Okay. The way I'd always thought about it was, if you think about the Hubel and Wiesel experiments, I don't know if you remember those. This is where they'd take a bar and run it through the visual field. Yes. And you would have these orientation selective columns, but they would selectively inhibit through lateral connections other areas in early visual cortex. And so the way that we had thought about in the beginning was that the trade-off, maybe you were getting some kind of spatial to frequency trade-off because of the spatial scale of the lateral projections of those orientation selective columns in V1. And so by setting up a bunch of bars, you might be able to change the frequencies. Now, I don't know, actually, Dora's been doing work since then, but I don't know what the newer hypotheses about that are. But
so we still think that it's these horizontal connections that in V1 that inhibit the same orientation columns. So we still think that that's part of the strong component that drives the gamma oscillations. But in a more general sense, we think it's a phenomenon that's potentially because we made a model that from the visual image predicts whatever you see, whether you're going to have a gamma oscillation or not from a large set of images. So you can basically run this model on a new image and see if what the chances are that you're going to see a strong gamma oscillation. And that model specifically uses orientation variance. So if there's only a single orientation on the screen and it's larger and higher contrast, it's going to drive a strong gamma oscillation. If there is more orientations in a particular patch that a population of neurons respond to, so this is really specific for the population receptive field of a particular region, then there's going to be low gamma if you have a lot of different orientations. And so even if you have an image, and it's not a grading, but you have a bar in a certain area, we saw that if you have an electrode and it has a very small receptive field right on that bar, it's going to have a strong gamma oscillation. So it's really this type of, so we think it's really this type of like single orientation within a receptive field. And those similar type of signals have been predicted by, for example, gain control. If you have a very strong type of input, which is a bar of a single orientation for visual cortex, then you have a very strong input signal. So there needs to be control of that type of input. So we think that it's related. And then just when you see a strong gamma oscillation, so we think in those cases that there's gain control that's related to kind of the gain control mechanisms in visual areas. And so if you have that type of signal in V1, it can propagate throughout, V2, V3, V4. But after, V4, we don't really see strong gamma oscillations as much. As far as we've looked.
Yeah. Very cool.
So I don't know if we're at a good spot to take a break, but they're seated and
yes,
they text us. Can we and then we can resume tomorrow. I'd love to tell you about working on understanding phone. Are you hiding, Otto?
Okay.
Sorry.
Okay. So Dora, your early work does include an algorithm to localize grid electrodes on the surface of brains based on photographs, I think, or CT and or photographs. Okay, and I think Kai, once you mentioned as well that you did create an algorithm to localize electrodes back in the day. If I remember correctly, you told me that in LA once. So did your paths cross similarly with before you guys met on an academic basis to work on similar problems, or how?
So actually,
this goes back in the past, but yeah.
So this was the first paper I published for my PhD, and that's actually when we met. We were working on that project together. So we were working on that project together. And we were working on that a lot, so we got a lot of chances to interact and work late evenings, etc. Because the first thing when I started my PhD, I was in the Netherlands for the summer for my PhD, and Kai visited for the summer. And because we were combining the electrocorticography data with the fMRI data, we needed to have a very accurate electrode positions on the cortical surface.
Sure.
In just millimeter coordinates that are co-registered with an MRI to be able to combine the data. And at that time, when ECOG was still like the most common modality rather than stereo EEG now, there was also this brain shift that we had to correct for.
Sure.
So we spent a lot of time talking about different ways to correct for that and how to project the electrodes to the pre-operative MRI volume, correct for the brain shift. And so we spent a lot of time just talking about linear algebra and then grabbing food together and then programming some MATLAB together later on. So it was a really fun summer,
cool.
Just working together. And
do you still use that tool? I think back in the day it used SPM5. I screened through it, so it's maybe a bit dated, or has it been developed since?
So it's actually still working. It's on GitHub.
Oh, cool. Fantastic.
And it's there are much better tools out there right now. There are several. There are portions of the algorithm that have been implemented in like larger tools that are like more standard in the field right now, but all the functions still work. So if you ever need something like a really good old basic tool that where you don't mind clicking through individual electrodes on all the individual slices rather than doing something that's much more optimized, like several other groups have developed, much more user-friendly tools. The basic principles still work, and we used SPM 12 at the time.
Okay.
And then we did a small upgrade to make sure that...
No, we didn't use SPM 12.
We used SPM 12?
No, because this was in 2008.
Oh, maybe it was SPM 8 then.
Yeah, so I had made an electrode localization, because when we started, we would have these 5 millimeter sliced CT scans.
Yeah.
And with lateral radiographs. And so when I started, we just wanted some way to try to infer something about brain position from literally lateral radiographs and operative photographs.
Yeah.
And so we would take the lateral contour of the skull, and like I wrote some MATLAB scripts that would let you basically stretch the brain to fit the contours of the skull, just like a simple affine transformation. Yeah. And then when I went to visit her because Jeff Ogeman knew Nick Ramsey and sent me there. So we actually have a picture from when I first visited of the day we met, which is pretty fun. And that was the year before I came from a summer. But that summer we were working on, the biggest problem with that I remember from the CTMR package when we were working on that was this. We wanted to be able to look at brains that were the actual patient's brains that looked reasonable. And they had high quality MRIs in Utrecht, but we had to extract like a cortical ribbon from that, and there wasn't like an easy tool that we knew of. Mm-hmm. So we were reading about like Voronoi tessellation, how you go from these voxels to an interpolated mesh. And it turns out there's a function in MATLAB called isosurface that made all of it really easy after whatever it was, 2 months. But that extraction of the mesh and like this Voronoi tessellation, and then discovering that there was some simple function that solves the problem in 30 seconds. That's the big technical thing. And then once you have those meshes, you can identify the orthogonal. You generate a smooth version of the cortical surface. Yeah. You can have orthogonal projections out to account for the fact that the brain has, when CSF is lost during the craniotomy, and you stick a grid on, has shrunk away from the convexity of the skull to try to project back to infer where the electrode positions would be on the brain before it shrunk away from the CT scan.
Super cool. Yeah. So since you mentioned late nights and talking about algebra, I actually asked Casey Halpern yesterday for a guest question for you, two of you. he was curious how your dinner conversations would be like. It is a bit off topic now. That was his question.
They're currently, they're all over the place, right? Because it's often like, what are we doing tomorrow? Do we have what do we need for groceries? What are the kids doing? Yes. So there's a lot of practical things that have to be dealt with. But in addition to that, it's sometimes like, I have this issue at work with these signals, and then, we get to talk about those things as well.
So I'm sure the kids love that.
Well, strictly speaking, I usually don't eat dinner.
Okay.
So, but our evening conversations are a lot of, I don't know, a lot.
Yeah, he's generally home too late.
The kids will talk about, Minecraft, and that's the big.
Of course. Yeah.
And then we watch a lot of YouTube videos with the kids. So we spend a lot of time just doing fun things with them, right? Like, do you know have you ever seen like Veritasium?
No.
Or Kurzgesagt? These are these YouTube channels about science.
Oh, great.
Principles in science. And we spend a lot of time with the kids watching those. And so there's a lot of general science discussions with the kids. They're at like the perfect age for that.
Fantastic.
Yeah.
Great.
And I don't know. A lot of ranting about the bureaucratic process of science.
Okay. And coherence.
Related to grants.
And
but and then there's talk about our work together, actually.
Yeah. Of course. Yeah.
Because our work is dynamic. It's not dynamic in the sense that you have a patient that's implanted, and I'm thinking about the clinical stuff that's going on, and she's been doing, research protocols with the patients, and she'll do clinical. So when we talk about work at home, a lot of times she'll do clinical tests with the grad students and so forth that then, I use as some secondary diagnostic techniques
Yeah.
for these patients.
Yeah.
To actually try to say, well, do we know about their functional representation? Is that going to play a role in limiting resections we would do, or where we put stimulators, that kind of thing?
Yeah. So going back to science, we have a good work-life balance even in this conversation. I think it's all mixed, right? So
Yes.
you mentioned you work a lot with devices and BCI. Currently have a grant with Cortex, or on the Cortex device from Freiburg.
Yeah.
Do you want to talk a bit about that and this interaction?
Yeah, I mean, I think right now there's this phenomena where you see lots and lots of different companies that are all, you hear about the Neuralink device and Synchron and, and the RC plus S device from Medtronic and these kinds of things. But it's sort of like a lot of things are done related to special access to these things.
Yeah.
And a notable exception to that actually is there's this guy, Tim Dennison, who had been at Medtronic. He's now at Oxford. He's trying to develop this open source PicoStim device. But what we're working on is trying to take the Cortex device, which is 32 channel sense and stim device where you can arbitrarily index channels back and forth for stimulation.
Yeah.
And it's a sort of fully implanted, but uses inductive coupling for power. I'm trying to take that and create an ecosystem by combining that with the BCI 2000 software environment that my friend Gerwin Schalk, who I think you know, who's actually been affiliated with our lab intermittently, and was one of my mentors for a long time. And then now Peter Brunner, who is his protege and really runs the whole BCI 2000 ecosystem, taking that and getting it working with the Cortex device so that no matter who wants access, there's a low barrier to entry to be able to have an arbitrary closed loop task that you want to do, or online signal processing task that you would want to do with patients in a simplified open source ecosystem. So actually, I mean, given what you've done and how useful Lead DBS has been for people to develop customized and tailored approaches to implanting stimulation electrodes, what we want to do is something similar, but in the hardware domain, where it's open source. People can take it, tweak it how they want, but there's a set of tools that sit there that lower the barrier to entry for people to be able to do these things. So we want to, like, it's really your philosophy, but in
EFIS and devices. Okay, fantastic. So the idea could be that people can buy the Cortex device for animal research mainly currently.
Well, it has some human approval, but it's currently going through it.
And before, but they could essentially buy it and use your software to do
whatever it is that they want to do.
Yeah.
And then there's some basic functionality that's there. So like for things like phase lock stimulation, for basic brain-computer interfacing, there'll be and for back-end control for assisted devices like for Tobii devices and WeGo devices. There'll be back-end control, so people, patients with disabilities already are able to use like eye tracker keyboards and this kind of thing. And this would make it so you could supplement the eye tracking, for example, for locked-in patients. You could supplement that with brain signals, and then as the ability to do eye tracking is lost, you'll be able to increase the relative influence in the signal that you're putting in to control these assistive devices with a brain signal. And so people will have back-end access into those into control of the Tobii devices and so forth from this BCI 2000 and Cortex brain interchange ecosystem.
Fantastic.
But they all will also have the full. This guy Peter Brunner at WashU has a full suite of modules for example, doing interacting with data gloves or motion sensors or controlling robotic arms. That's all already built into this ecosystem.
Got it.
So it really would let people have just a rich library that they could use, but it's all open source. So whatever their functionality that they want is, they can take what's there and it can be tweaked. And then as a group, we will try and help people to do it everywhere. So the idea is to play some support role, much actually like you've done with Lead DBS, we want to have a hardware version of that. And so it's a multi-PI initiative with Peter Brunner and this guy Greg Worrell, who's a neurologist where we are.
Is it tied to the Open Mind consortium of Tim Dennison et al., or like interact? Do you guys interact with that?
So Peter Brunner and Greg Worrell interact with Open Mind.
Got it.
It's not explicitly part of our research initiative, but so two of the three PIs interact. I'm bandwidth limited as it is, but yeah,
of course. And then for indications with that device, the company or you and or both would think of epilepsy mostly, or PTSD, or what do you think will be the first lowest hanging fruit to bring into actual therapy with this?
There'll be epilepsy indications, I think, that are initially treated with this. So things like detecting HFOs online and stimulating in response, these high-frequency oscillations you see in epilepsy. There's a guy, Nuri Inche, who's a bioengineer that's now at Mayo, he has a separate U grant from the NIH to do that, and he came to Mayo with that grant. Sort of we have this critical mass of people or something. Yeah. And I think that'll be initial indication. We want to use it to help patients with ALS. So Mayo is one of the largest ALS treatment centers in the country, and we work with Nathan Staff, who directs the ALS clinic at Mayo. And so at the conclusion, when we have this device working well, and we have these applications working well, we'll immediately apply it to help the patients in this clinic with the rudimentary BCI. So actually kind of what Nick Ramsey did in Utrecht with the Medtronic Percept device, or at that time it was the PC plus S. It was the non-rechargeable one. And then we will, and that was, one or two dimensional control, and we'll have a little bit higher dimensional control, but it's really extending his work. And the idea is we want to have a cohort that we work with. So we don't want to be the fanciest tech demo on the front page of the newspaper kind of thing. We want something that will be able to help patients where we are now. Yeah. And that's kind of fun.
Absolutely. Yeah. You mentioned yesterday that many of the current tests where they, for example, controlled a robot arm were just in the lab, and there was no real treatment benefit in most of these existing examples.
So I think brain-computer interfacing, the real question becomes, at what point is this something where the motivation, I think, is relatively unimportant, but where the end goal of what's being undertaken, whether it's science or clinical, is to provide patients with a service that they can use to help them in their day-to-day lives. And I hope that more of the brain-computer interface community will actually be doing this. Yeah. Right. I think. I think right now you have the Synchron device where they have this endovascular electrode, so it goes into the superior sagittal sinus. By virtue of where the stent is placed, I think that initially, at least, there's a couple degrees of freedom, but their goal is to treat patients now. Yeah. And I like that. I think that's noble. I think that a lot of brain-computer interfacing has been plagued by a motivation that has to do with scientific understanding and also career advancement, if I'm honest. And I think that's been something that has limited the pragmatic improvement of devices that would help people. Yeah. And instead, you have a lot of very fancy tech demos where the people that participated in those tech demos have never had free use of a device. And I think that that should be more transparent scientifically. Yeah. I feel like the motivations of many of the people involved are not what is advertised, because at the end of the day, they haven't provided people with a therapy. And if you're going to be implanting things in people, I do feel very strongly that there should be some, at least, ancillary benefit related to what they're doing that's in some way independent of the science that you want to do and publish. Yeah. And I don't know that that's been the case, with the notable exception being Nick Ramsey's group in Utrecht, and now I would say this Synchron device where...
Yeah. It sometimes has this feel in general in science where, it's a bit like a theater. You build up all the stuff and then make one picture for the paper, and then after that all falls apart again, right? And engineering in industry is very different, where you actually want to build something that works. And I also always try to go more towards that and really try to make something that works and build upon it, right? But I feel like sometimes,
Andy. I mean,
well,
at this whole meeting,
it's tough, but
everyone loves what you've provided for the DBS field.
But I feel like you have the same philosophy, right? It's not about essentially just showing it once, like a proof of concept, and then all falls apart again. But you want to build something that actually helps people, right?
Yeah, and I think separately from the idea of helping patients, there's also scientifically, you should have the philosophy that the work that you do should be able to be reproduced by anybody, and you should have the maximum degree of transparency possible.
Yeah.
And so, like for Dora, that's been a big thing for her. So she's doing, this data standardization with BIDs, which is makes it so that anyone around the world can access those data and at some point take the data into a usable form. And I do feel that when you publish these data, particularly if you have patients that have volunteered, that you of course fully anonymize everything, but you want to maximize the utility of scientific understanding that's going to come to that to the widest degree possible. So all your data and your code should go up with your papers.
Yeah, totally agree. And so in this space of interfacing, the interaction with industry is critical. Without it, it would not work at all. I think you both do some consulting. I do too. You can't talk about that, I know, but maybe you can talk more general about the importance of the interaction between industry and academia. That and what's your take on that?
I mean, Kai has more interactions directly due to his practice as well. Like in his practice, he interacts a lot more with devices that he implants for patients' benefit. I think it's very interesting for those interactions to see what your techniques can possibly be used as maybe in 5 or 10 years. Such that if you do, that's the advantage about working in a hospital in general, is that you can collaborate with clinicians who have specifically relevant questions. And so even though my scientific efforts are relatively fundamental, you see where they can be used in a number of years, and all the tools, for example, that you provide, or the code snippets, can be then used in several different settings. And I think that's the same with companies. They're interested in using these things, or actually applying these things. But Kai has more interactions. For example, like what he just described for the brain-computer interface work.
So most of the interactions that I have with companies are not. Well, I haven't had any. I've never had $1 from a company ever. Yeah.
Oh, okay.
So the interactions that I have are more co-development kind of a thing.
Yeah.
So, it's difficult because companies have to respond by definition, especially if they're a publicly held company. They have to respond to incentives.
Of course. Yeah.
And so, I didn't really understand for a long time. So I started talking to them that, things like the ability to patent something. I always thought, well, look, you put it in the public domain as fast as you can, and then anyone can use it, and any company can build whatever they want. The problem is that if they don't have any kind of exclusivity, then a lot of times they won't pursue things, and I don't know where the best balance for that lies. Yeah. I do think there's this, there are these NIH initiatives now, like the Blueprint MedTech program, where, and like we have, our grant where we use the Cortex device is not Cortex. It's not a co-development grant of any kind. We just buy their devices, and then we're in the integration with the software on the side. But we're working with companies like, I don't know if you've heard of Neuronexus. They develop, these high-density electrode arrays, penetrating electrode arrays that primarily been used in animal experiments along with amplifier systems. And, we're working with them to develop things. I feel like that, especially as part of Mayo. So Mayo's pretty cool in that regard, that like I can work with the companies, and then hopefully Mayo and the companies can have some kind of agreement, and I can not have that be part of anything I think about. I think that's a little bit idealized, but this idea that you can just work with them as collaborators to develop something, I think is important, because the curse of the engineers when you're dealing with engineers and doctors is that the engineers try to tell the doctors what they need. And then when you're like, there's some classic examples with that I've seen where you use these navigation softwares and you go to the people in the company, you're like, I want it to be able to do this thing. Mm-hmm. And you can draw, like, you don't have to draw, we can take, sort of lab software that we've made, and can you just integrate this somehow? And they say, no, you don't need this. And you're like, well, we're doing this already. I mean, I guess you get the irony, right? Because lead DBS, and you say, well, like this thing works, right? Like we're able to do whatever task it is that we want with this. Can you just add this functionality? And it's like something trivial, and you'll have engineers tell you what you don't want. So I think maybe if you
I love it. Okay.
If you get involved with companies earlier, maybe there's a way to work together. And then the other thing is that a lot of the people that are associated with the space that we live in, who are companies, left academia at some point to start these companies. Mm-hmm. So that's the case with Cortex. That's the case with NeuroNexus.
Yeah.
There are a few notable, like Tim Dennison's an example of the contrary, where he left industry to go into academia and has been able to accomplish things there. But I think he's also a pretty sort of exceptional individual.
Yeah.
Have you met him before?
I have not. No, I've been meaning to ask him to come on the show as well, because he would be.
He would be a great person to have on the show.
Yeah.
He would be great. Yeah. And he's a really, really fun guy. He lived in Minnesota and then went to Oxford.
Cool.
Yeah.
So I want to be mindful of your time, so maybe we can stop with some rapid fire questions. Feel free to answer briefly, but of course, if there's more to say, you can also take longer. What does the operation room of the future look like?
Rapid fire question.
Blue.
Well, I would say that I think the operation theater of the future has a lot more. It's a lot more multidisciplinary and a lot more integrated with technology than the ORs now. And I know it's very catchy to say that, but even since I started my practice, like the idea of robotics and neurosurgery that's now the standard, right? For at least for certain types of surgery that we do, imaging software is more standard. And I think that the operating room of the future requires a technical expertise that I think, we have to start thinking about, like, should we be pulling all the doctors from biology, or should there be more of an emphasis in selection of people who will go to medical school from people that come from different backgrounds? And actually, I guess since you come from the European system, well, actually you have a PhD. How did that work? Because it's harder to do in Europe than it is here.
Yeah, well, I'm not sure. We usually take some shorter, so it's more like 4 years in Europe usually, and it's in medical neurosciences, so it is very close to what I've been doing anyway. So
okay,
yeah. Eureka moments in your career, or things where you thought, oh, now I understand it, or that was a great success, or what was moments like that.
There were, I'll describe two. So the first was when we finally had all the intracranial EEG pulled in together with fMRI data, basically matched from each electrode, and we could, across patient, within a couple of patients, see that spatially how the fMRI signal correlated with ECOG, and that there was a really strong correlation between the broadband signal and the fMRI bolt signal, because I had these big discussions with my PhD advisor Nick Ramsey about whether it would be low frequency decreases or the high frequency increases that would correlate with bolt. And we didn't know until we actually could see that it was locally really the high frequency increases that correlate most strongly with the bolt signal, and more diffusely that the low frequencies explain additional information. But that was kind of like, we have it now. We have something that's extremely consistent. The second one...
Broadband captured at high frequency.
Broadband captured with high frequencies over 60 hertz, basically. The other thing that was like a eureka moment is when we were looking at these narrowband gamma oscillations in visual cortex. And there was, and we had this difference between, we started looking at more complex spatial patterns, basically with these curved lines. And in general, the curved lines did not induce narrowband gamma oscillations. But there was a couple of electrodes, 2 electrodes in one patient, where these curved lines induced narrowband gamma oscillations. But then we calculated the population receptive fields of those electrodes and overlaid those on the curved lines. And we could see that the population receptor fields were so small that within the population receptor field there was basically only a grating. And so then we thought, like, if it's like this detailed, like, we really have to capture the population receptor field and look at what is the content of the population receptor field. And now we can explain this variability within patients. It's really these like straight lines that we can predict, also use for a model to predict these narrowband gamma oscillations. So those were two like really cool findings when we thought, like, now we have something that's actually really there.
Yeah, fantastic. Do you have any key moment like that, Kai, in your...
A couple. I mean, so we had this, we talked before about how we went looking for gamma oscillations, and then I was talking with my thesis advisor, Marcel Denise, and I was showing him these things, and I was like, it's not, there's no real evidence for oscillations. And he's like, well, why would you start out thinking that there would be oscillations at all? And then that's where this 1/f and broadband story came from. And that was maybe Marcel's aha moment, and he was truly, like, that's amazing. And I think this idea of oscillations in motor cortex, I went and found that there was rhythmic entrainment. I'd read a paper from Ryan Canolti about this idea of having, they called it theta-gamma coupling, but really it's this idea that you have local brain activity with broadband, reflected by these broadband changes in the macroscale potentials we measure. And I said, well, let's see if these things exist in motor cortex. And there was entrainment that was there, and it was clear that this entrainment was going away when you engaged in movement. And so from that, I thought, well, I mean, we'd known from Peter Brown and some other people that they thought that oscillations were somehow suppressive, but there was this idea that I still think is an amazing idea, and I think it's sort of entered in the background of how people think about these things, but I don't know that it's quite caught on. But we had this idea of suppressing neuronal populations by synchronizing them, and that rhythmic entrainment was the biomarker of this, and I think seeing that in the data and just saying, wow, there's this thing, right? And there's rhythmic entrainment. It appears to be a mechanism for suppressing cortex, and that doesn't have to be a direct inhibitory input. You could actually just, anything that synchronizes a neuronal population will reduce the amount of computation that population can perform of neurons. Yeah. And so this was a general mechanism, and it's something that now that I have my own lab and so forth, I want to go back to, and we've been collecting data for this. I mean, there's a number of aha moments.
Yeah.
I guess clinically the biggest one was, I wrote about this in my applications to residency. There's this guy, Phil Starr, who's in San Francisco, and I went to do a sub-internship, which is in medicine, is your training when you're a medical student before you do residency, and spent time at UCSF. And I went with him to his clinic, and he said, I want to show you something. And he shows me this video of this kid who's just wrapped up like a pretzel on the ground, having to crawl in order to get across the floor. And he's like, you're going to see this patient later today. And, then 5 minutes later, after seeing the video of this kid, the kid walks in, runs across the room, and gives him a hug. Fantastic. And I thought, this is the most amazing thing I've ever seen. Right? DBS is magic.
In dystonia, absolutely.
And so I'm really excited because this was the thing that for me was like I'm not a religious person, but this was like a spiritual moment. I was like, this is what I want to do.
Yeah.
And I think that for me, that was when I thought, well, movement disorders, and treating kids, this is amazing. So for me, that was a clinical moment. And then every time, I'm sure you've been in the DBS cases, and turn the stimulation on, and the tremor goes away. Like that doesn't ever get old. Hundreds and hundreds of times, and you still get goosebumps, even when you at least sort of know how these things work.
Yeah.
And you do them all the time, it never gets old.
Fantastic. Yeah, I agree. Any advice for young researchers or clinicians entering the field, neuroscience or neurosurgery?
Work on things you find interesting.
Yeah.
Work with people that have similar scientific interests and are interested to talk about the science with you on that topic. And that basically give also another supportive in that sense to support your scientific development. I had like very great relationships with these mentors that I mentioned, like Nick Ramsey, John Winnower, and Brian Waddell, and they all had very similar interests in terms of what we were interested in, and with all of them I had, very long conversations on these topics and how we would capture these different signals and describe them. And I think that was, and they were all also extremely supportive, career-wise, supporting when I was in the US and got pregnant and had to finish my PhD remotely. Having 2 kids during a postdoc, sometimes having just to stay home because you have a sick kid at home.
Yeah.
Transitioning between postdoctoral grants, all those things. If you have a supportive environment with the same interests, that was extremely helpful throughout my career.
Yeah.
And develop your own code, learn how to code, and then support people who start out.
Makes sense.
Which is definitely helps progress.
I would say 2 things. The first is people early in their career and maybe even later should focus as much as they can on the development of a set of fundamental tools. Mm-hmm. Okay, try to understand whatever signals you're measuring, and put in the hard work up front. So rather than, it's important to focus on the technical details of how you do science more than how interesting the problem is working on. Yeah. I think, especially early in your career, right? The best science is unanticipated, right? The best results, I think, or most of the most inspiring results we know about in science have come when people weren't looking for them.
Yeah.
But they were doing very, very careful measurements and trying very carefully to reduce those measurements to some simple statements. And then the second would be to find a confrontational environment. Okay. So you don't want to have hostile interactions, but you want to be able to have arguments, and you want to be interacting with people where you can be adversarial about the same concepts, and you want to be able to be convinced, and you want to be able to convince the people that you're interacting with, because that forces you to articulate your ideas well. And I think it's how the best science is done. So you want to pick an environment to work in that is confrontational
but supportive. If we mention
I think in terms of like the supportive environment, a supportive environment is an environment that asks a lot of questions, right? Because that's what you want to learn as a student. You want to learn how to think about these things. So you want someone who asks a lot of questions and asks you to look at all the raw data, to look at every single trial of your measurements. Yeah. Always look at those data. So you want, and that is a way of that I think of as supportive, rather than Kai may describe that as confrontational. I may describe that as just having a lot of questions.
Yeah.
But then
I think it's not exclusive. The 2 points, right? You can be supportive in a career perspective, but then confrontational in the content and scientific development, right?
But then I'm also Dutch, so I don't know whether what Kai calls confrontational is for me just normal interaction.
Look, when you're giving a talk, and if somebody comes up to you at the end of your talk, or if they get up at the podium and asks you, regardless of what their internal motivations are, if they ask you a tough question, that is actually a tough question, and not just being hostile. Yeah. Look, that person was paying attention to what you had to say. Exactly. I remember early in my career, I had there's a guy named Tjeerd Boonstra who had written an article. He was in Australia. He's a Dutch guy who was in Australia, who worked with Michael Breakspear, and he wrote an article when we found this power law stuff, saying, well, another different way to do it that would probably be better would be to look for something called the Hausdorff dimension in the time series data that we measure. And at the time, I was, because it was somewhat, somewhat critical, and maybe there's a better way to do it. I remember talking to Marcel Denis and Larry Sorensen, these 2 physicists I worked with when we did that work, and I was like, oh, we should write some letter back, and they said, well, you should actually be like, somebody cared enough about the stuff we did, like that.
Exactly.
You're lucky that people would read your work, spend enough time on it to understand it, and then do this. Like that. Yeah. That's you should be grateful. Yeah. So I've always been grateful. This guy, Tjeerd Boonstra, because of that.
Yeah.
I've had one conversation with him in my life, but I always remember,
No, I totally agree. Yeah, it's much much easier to get ignored in this field of so many papers and so on.
Yeah.
So it's always a good thing if people react to your work. I do agree. Yeah.
Yeah.
Dora, any advice for women in neuroscience or academia?
So, one of the things that I've heard that is that I do more naturally maybe than others is to learn how to sometimes interrupt. Not interrupt people in a mean way, but if you feel like you're being ignored in a room, you can just speak up. If you have a valid argument, it will be listened to. And I think that that's something that people often don't feel like they can do, or they feel like someone else is maybe talking too loudly. Well, in those cases, it's really helpful to make sure that you ask your question, maybe not interrupt in a mean way, but in a nice way. Yeah. The other thing is that when, as we just were discussing these types of critical questions, ask if people give you critical feedback. That's generally a positive thing. So I really benefited from the critical questions that people asked, and even though they don't always make you feel good about what you did in the past, you have to go back and think through the problem and then come back with something better. Yeah. So I think you just have to think about what the source is of why people are asking these questions, and you can always come back with. People always trust the science in the end. Good mentors that I've worked with generally trust the science, and so I've had a really positive experience with those kinds of things, and speaking up.
Yeah,
sounds good. You don't get to comment. We don't get to comment, I think.
Well, the only comment I would make is that if you're anybody and you're in an environment where when you say something, people discount you because of something that's independent of the content of what you've said, that's an environment to get out of.
Yes.
Especially in the modern world, there are plenty of environments where people will take you on the merits of the content of the thing you're doing rather than the
whatever else.
Yeah.
Great. Yeah. The future of the field. I asked about the future of the OR already, but the future of the field of neuroscience, invasive neuroscience, neurosurgery. What are the big next things that will be on the horizon, in your opinion?
I think for these stimulation type of studies, we'll start to see these. I mean, I'm really excited to see these biomarkers for specific networks. Yeah. So I think we'll get much more detail incorporating, detailed anatomical studies that are happening on the one, and more detailed imaging with these types of electrophysiology studies, where you get really very detailed understanding of the network, the area you're measuring, the area you're stimulating, and what type of responses and interactions those types of networks should have in an individual subject. I think that that's where there's going to be dramatic advancements in the next decade or so.
Anything to add, Kai?
I don't know. I like to think about I'm a small scale thinker, not a big picture thinker. I just want to find the fun data to work on and then let it show us what it'll show us.
Yeah. And then are there any missed opportunities, though, that you think we should be doing as a field, like not the three of us, but the entire field, that we're not taking enough these days? Or
yeah, I think we need to de-emphasize the flash. And I think as a community, people
Flash?
Flash means sort of the notoriety, right? It's like the people call it the Superman phenomena, where you have these environments where you have these huge personalities, and then you have, these results that change everything, and yet they're never reproduced. And there needs to be an emphasis on reproducibility and rigor. And I think that the rhetoric is very strong for that, but the trend is not.
True. Yeah.
So the rhetoric is growing that that's how things should be, but then the rhetoric is not matching reality, where there are big things that happen that are never reproduced.
Yeah.
So
they get a lot of attention.
Yeah. I mean, in terms of that, I think also we need to start taking apart the brain-behavior relationship, because the big picture things that you're talking about are correlations between networks and behavior. Now, if we think about that in more detail, like what makes that relationship, it is processing times in individual regions, inputs through the visual stream, things spreading from visual to cognitive areas, cognitive output, cognitive region sending a motor response to a button press. We need to start breaking down that relationship into like lots of little details that make that up, because otherwise we can never, I think, explain the variability that we see in terms of behavior. So I think we have to start thinking about these boring details much more specifically, rather than this big picture. Take it apart into little details, such that we can actually start quantifying these things in a much more specific way.
Yeah, so more rigor, less flash. Yeah, I get the point. Yeah, I very much think so. There's so much incentive also monitoring any single Nature paper, right? And so there's it's hard to break that system in a way, right? But we should very much agree.
Yeah, we should be persuaded by data argument. We should be persuaded by data rather than by charisma. Yeah. But that's true of life in general.
Yeah. But cool. So then, thank you so much for taking so much time, and it was a great honor to talk to you.
Yeah, thanks a lot.
Thank you very much.
Yeah.
Thank you.